So the second part of week 8, we're going to look at mass movements. So in order to have a mass movement, you have to have some kind of slope. So all material that moves on the landscape that's determined to be a mass movement has some kind of slope. And the slope is kind of a delivery surface for transporting things from one place to another. So when we look at a slope, the idea is that the material is overcoming some inertia, some threshold, and the inertia might be cohesion or weight, and it overcomes that and is able to move down under the force of gravity. So the steepness of the slope impacts how much material moves and when material moves, and the steepness of a slope is often determined by the texture of the material on that. We use the term angle of repose to indicate how steep colluvium or dry material will create when it lands in a pile. So if you look at a sand dune has an angle of repose, dry sand of about 30% angle. And very coarse angular material can have a much steeper angle of repose. So in order to get a slope to fail, you need to have the driving forces, or whatever's on that mass of soil or sediment, to overcome the resisting forces. And so the size, the weight, the shape of that material is going to have a lot to do with the slope failure. Also the amount of moisture and the steepness of the slope. All of those things are going to come to play. So we can look at a little equation where when we identify what are the driving forces to get slope to move, so or to get a moving block or a sediment to move. And so the driving force is just kind of gravity, and it is the slope. So the steeper the slope, the easier to get things to move. If you have liquid on a slope, if you have water running down between the cracks, it can actually lubricate and get material to move. The resisting forces are the forces of friction. There's natural friction between things. Think about if you rub a piece of paper back and forth across a desk and you tip that desk over or tip it up, that paper can stay on that desk for a little while as a result of some friction. But if you tip it too far, at some point it's going to fall off. So the resisting forces can be cohesion or natural stickiness of the soil or the rock. It can be the weight of that rock moving perpendicular to the Earth's surface, so that has some amount of adhesion just to hold that material in place. So in order to get the driving force to overrun or to emphasize the resisting force, one thing you can do is to make that block of sediment heavier, and water will do that. You see a lot of slope movement when you have in a wet season or in rainy weather. You can break that friction or that cohesion with an earthquake. You can break it with water flowing underneath. If you increase the slope, you can overcome the resisting forces, and you can increase the slope slowly over time with tectonic movement. You can increase it with an earthquake, which would have crustal rebound that would break that right away. Another thing, especially here in the Northwest, is you see the resisting forces being overcome after logging. Often the tree roots help hold soil and material in place, and once those are removed, then water and water pressure can actually help things move down slope. So when we look at mass movements, we can look at them as fast or slow, saturated or dry. They're often very complex. They can start out as one type of mass movement and then end up as another type of mass movement. We're going to look at rock falls and topples, debris flows, and translational and rotational landslides. So just a bit about the Oh, that slides a little bit out of place. So looking at if the resistance force is greater than the driving force, you're going to have an element stable on the landscape. If the resistance force is less than the driving force, you're going to have slope failure. Sorry about that. I should go ahead and move that up for next time. Okay, so the fastest type of movement is called, I can move that down a little bit. Maybe, oh shoot, hold on a sec. One of those days I'm having a love-hate relationship with technology. So the fastest kind of mass movement is a fall. A rock fall drops off kind of an over steep cliff. You would see that often when you have frost wedging, kind of would finally break that joint, and gravity would win. It falls free, not in contact with the slope. It may bounce and topple and knock stuff off on the way down. A topple is just kind of when rock falls over, it doesn't move very far. It may stay in contact with the slope. And you've all seen those signs when you're driving along the highway, watching out for rock fall. Very common in the U.S. And we also, you may not get a warning, so this is a great example of a rock fall. Kind of loose, you can see how granular this material is. If you look at the slope, it looks kind of, I would call it kind of weathered. It's rotten, it looks very granular. I can see a lot of loose grains and then big fall down on the roadbed. Talus is a special kind of material. It's formed from colluvium, which is kind of loose, unconsolidated sediment, and it is created by the deposits of water washing that stuff out of a watershed or rain shed. And so this is probably colluvium, dry material that's been kind of flowed out of this canyon. On the other side is, actually that's probably needs to go right over there. The Talus Slope is this cone-shaped material at the bottom or the base of a cliff, and it's just collected as rocks fall off that hillside or cliffside, and it creates a very predictable angle of repose and a very predictable shape along the base of cliffs. A landslide is a sudden rapid movement of material, and when we're talking about a landslide, we are not talking about water being involved in the saturation of the movement of that material. There's two types of slides, a translational slide and a rotational slide, which is also known as a slump. When you're looking at a landslide, there's a couple components that help identify what kind of slide it is. One is the headscarp. That is kind of the top of the landslide, or where the movement, the first crack happened, so that above the headscarp is original non-disturbed material. Below the headscarp is the body or the material of the deposit. At the very end of the landslide is called the toe. And looking at the shape of the toe and how far material flowed or slid can give you some information of what type of landslide it was. And the material in the middle tends to create a very bumpy, uneven, hummocky landscape. You may see if trees are still in existence, they kind of are tilted in different directions. There may be ponds caught up back in behind these slides. So let's look at the first one is a rotational slide or a slump. When you look at a rotational slide, looks as if the bedrock has just been pulled and slid backwards a little bit. There's kind of a curve along the rock base. You're going to have a back slope, a lot of water. They are about as wide as they are long. They're almost blocky in size. Generally, there is a lip or a higher edge to that, and there's no toe. They don't flow very far. So here's an example of a rotational landslide. Let me just fix my toe here. So there's my headscarp, and you can see that this curved um, movement of the sediment just kind of rolled backwards. The trees that were originally on the surface have dropped down a step. This could be even considered a bit of a terrace. Sometimes you'll have multiple steps. Um, there's can be water held in the back of this pond. The toe is kind of rubbly. It doesn't go very far. Here's another example of a backward slide. It's about as long as it is wide. You can see those red crosshairs. The original material may not fall very far. And again, ponds and backward rotation. So here's an example of a slump. So here's the original elevation surface. It just kind of slid back. And this may be the lip. It may be a little higher than this backwards part, which would collect water. There's another example looking at the terraces. So here is the headscarp. There's the first terrace. There's the second terrace. Another slump. The house just kind of fell down about 12 feet. You can also begin to see beginnings of landslides along street cracks. You'll see on a steep side of a road, you'll begin to see these road cracks, and this is something that road crews often spend a lot of time trying to fill these cracks. If you can get tar in them, you can keep water from seeping in, which would lubricate or kind of remove that cohesion and maybe have the slope fail. So that's why you see a lot of road crews, a lot of tar being added to those road cracks. There's a road crack that just slumped down. There's another one, again, didn't go very far. We don't know what the toe looks like at this point, but we can see kind of the scarp and the beginning of that fall. Okay, of that slide. A translational slide, however, you can see is dramatically longer than it is wide. And that's one of the classic elements of a translational slide. It also has a much bigger, well-developed toe. This is a Slumgolian slide out of Lake I forget the name of that lake, Cristobal Lake. So as landslides aren't including saturated water, flows tend to have water saturation, or that it's very moist. The material is kind of almost liquid. You can have an earth flow or a mud flow, and they can be fast or slow. An earth flow can be very saturated but move very slowly. A mud flow can move very fast. And you can have a translational slide that is also a mud flow, or a translational slide that is also an earth flow. And then you can have a debris flow, which means that once the material gets into motion under the contents of water and saturated soil, it picks up more rock, it picks up more rubble, and becomes almost this huge bulldozer. So here's an example of probably a mud flow, very fast, very liquid. I'm sure these cars did not see this coming. And these can be very damaging, and you're going to look at a couple examples this week of different types of mass movements. The slowest over time movement is called creep. Creep is just the downhill movement of soil particles over time, and this can happen by just overcoming slope through roots or through freeze-thaw cycles, lifting up little bits of sediment. And over time, it just results in kind of downslope movement and the tilting of trees and of fence lines. So here's a tree that is a bit curved at the base. That's often called a gunstock tree. Historically, these trees were searched for because they had this natural shape and curve to the wood grain that could be used for ship bows or for gunstocks. And this is just as a result of phototropism, where the tree is trying to straighten itself up and be perpendicular to the ground for reaching sunlight, but it curves as the ground moves below it. Another example of creep is this fence line, which you can see is kind of slowly tilting out over time. So being able to look at the different types of land movements, being able to understand the shape of the landscape depending on different landslide types is kind of the focus of this chapter.